Right now, without moving, without doing anything at all, your feet are aging slower than your head. Not as a metaphor, not as a figure of speech, as a measurable, confirmed, physical fact. The bones in your skull have ticked through more time than the bones in your feet every single second of your life, because the floor beneath you sits deeper in Earth's gravitational well. And gravity, it turns out, doesn't just pull things down, it slows time itself, and we can prove it. A tower in 1959, airplanes carrying atomic clocks around the world, a cloud of strontium atoms 1 millimeter tall, all of it pointing to the same unsettling answer. Get comfortable, subscribe if you're new, because by the end of tonight, gravity will never feel ordinary again. Part 1. The room is not running at one time. Right now, without moving, without doing anything at all, you are living proof that time is not what you think it is. Sit with that for a second. You are in a room. Maybe you are lying down, maybe you are seated, maybe you are standing in a kitchen at some hour of the night that you would rather not admit to. And in this room, at this very moment, time is running at different speeds in different places. The floor beneath your feet, or the surface closest to the ground, is running slightly slower than the air near your head, not slower in a poetic sense, not slower as a figure of speech. Slower in the way that two atomic clocks, one placed on the floor and one placed on a table, will show genuinely different elapsed times after a single day. The floor clock will have ticked fewer ticks. The table clock will be ahead of it. And neither clock is broken. Neither clock is wrong. They are both correct, and they disagree. And that disagreement is the universe telling you something that Newton never had to say. Time is a property of place. This is not a new idea. It has been confirmed in labs, in aircraft, in orbit, in the steel towers of Harvard, in optical lattices cooled near absolute zero, and in the satellites you use every single day to find a coffee shop or navigate a freeway. The bending of time by gravity is not a theoretical curiosity. It is a measured fact, an engineering constraint, a component of devices you carry in your pocket. And yet most people go their entire lives without ever truly reckoning with what that means, not just for the GPS satellites, not just for the physicists, but for them personally, standing in their rooms, with their floors and their ceilings and their bones aging at rates that are not and have never been the same. So let us start there, in the room with you. The floor of wherever you are sitting right now is closer to the center of the earth than your head is. If you are a typical human height, say 1.7 meters from floor to crown, then your head is 1.7 meters further from the earth's core than your feet are. That sounds obvious. It sounds trivial. But in the language of general relativity, that 1.7 meters is a difference in gravitational potential. The floor is deeper in what physicists call the gravitational well, the region of space-time that has been curved by the presence of mass. And in a gravitational well, time runs slower as you move closer to the source of that curvature. The effect at human scales is extraordinarily small. We are talking about a difference of roughly a few hundred picoseconds over an entire human lifetime between the top of your head and the soles of your feet. A picosecond is 1/trillionth of a second, so the accumulated difference over 80 or 90 years of living is on the order of billionths of a second. This is not going to show up on your birthday cake. Your feet are not going to age visibly differently from your face because of gravitational time dilation alone, but the fact that the effect is small does not mean it is zero, and it does not mean it is undetectable. In fact, since 2022, it has been detectable across a distance smaller than a grain of rice. We will get to that. But first, the more important question: how is this possible? To understand why gravity bends time, you first have to let go of the way you probably think about time. Most people, if pressed, would describe time as a kind of river. It flows, it moves forward. It carries us along with it. The universe has a past, a present, and a future, and time is the thing that separates them. Marching steadily at the same pace everywhere, the same beat in Tokyo as in Buenos Aires, as in the outer solar system. This is the Newtonian picture. It is elegant. It is intuitive. It is also completely wrong. In Einstein's general theory of relativity, published in 1915, time is not a universal river. It is not a background. It is not a stage on which events happen. Time is part of the structure of space-time itself, and that structure is shaped by mass. Where there is more mass, space-time curves more strongly, and one of the consequences of that curvature is that time runs at different rates in different places. A clock near a massive object, near a planet, near a star, near anything with significant gravitational pull runs slower than a clock far away from that same object. This is gravitational time dilation, and it is one of the most precisely verified predictions in all of science. Now, here is where it gets strange, and this is the thing I want you to really sit with. It is not just clocks that run slower near a gravitational source. It is everything, every physical process, every chemical reaction, every electron transition, every heartbeat, every neural firing, every metabolic process that constitutes the physical fact of you being alive. Near the bottom of a gravitational well, everything that takes time, which is to say, everything happens slightly more slowly than it would at the top of that well. This is not a mechanical effect, like friction slowing a clock. The very medium in which these processes occur, time itself, is running at a different rate. Your body is running at multiple rates simultaneously. Think about that. The neurons in your brain, the enzymes in your stomach, the cellular divisions happening in your bones, all of these are physical processes, and all of them are occurring at rates tied to the local passage of time. Your skull is a few centimeters higher than most of your organs. The atoms in your brain sit in a slightly weaker gravitational field than the atoms in your feet. And so time, for the atoms in your brain, ticks ever so slightly faster than time for the atoms in your feet. The difference is unmeasurably small in any practical medical sense. But the principle is not small. The principle is one of the most profound things physics has ever uncovered. There is no single time rate that describes your body, because your body exists across a gradient of space-time curvature, and every layer of that gradient is running at its own local rate. We have a word in physics for the time measured by a specific clock at a specific location, proper time. Your proper time is the time measured by a hypothetical clock that moves with you at your location. But because your body is extended in space, different parts of it have different proper times. And because the Earth is a massive object curving space-time around it, your proper time at sea level is different from the proper time you would experience on a mountain or in orbit or in interstellar space. The question of which time is the real time, the true time, the universal time, has a clean answer in modern physics. There is no such thing. There is no master clock anywhere in the universe. There is no privileged observer whose watch reads the correct time. Every clock is local. Every rate is relative to its position and velocity. The universe does not have a single ticking heartbeat. It has billions of trillions of them, each slightly out of sync with the others, depending on where they are and how fast they are moving. This is not a limitation of our measuring tools. It is the fundamental structure of reality. Now, if you have never encountered this idea before, it might feel abstract. It might feel like something that only matters for particle physicists and astronomers working on exotic objects far from everyday experience. So let me bring it back to the floor of your room. Optical lattice clocks, the most precise timekeeping devices ever constructed by humans, can now detect the gravitational time dilation caused by a difference in height of just 1 centimeter. 1 centimeter. The width of your fingernail, If you place one of these clocks on your floor and another on a shelf 30 centimeters higher, and you let them run for a day, the floor clock will be behind. Not by much, we are talking fractions of nanoseconds, but the difference is measurable. The National Institute of Standards and Technology, NIST, has done this. The clocks disagree. The room is not running at one time. This has implications that extend far beyond the laboratory. The fact that every point in space has its own time rate means that time is not a uniform background against which events play out. Time is a property of the geometry of space-time, and geometry is shaped by mass, and mass is everywhere. So time gradients are everywhere. The gradient in your room is tiny. The gradient near a neutron star is not tiny. The gradient at the event horizon of a black hole is so extreme that, from the outside, a clock falling toward it appears to stop entirely, not because the clock breaks, but because time at that location, relative to an observer far away, has slowed to zero. But that is not where we start. We start in 1959, in a tower at Harvard University, where two physicists named Robert Pound and Glen Rebka decided to test whether gravity really bends time, not with satellites, not with billion-dollar instruments, but with a source of gamma rays and a steel tower 22.5 meters tall. And what they found permanently changed what we know about the nature of time. Part 2. The first measurement of bent time. There is a particular kind of boldness in setting up an experiment to test a prediction made 44 years earlier by a man who was already considered a genius before most people alive at the time were born. Albert Einstein published the general theory of relativity in 1915. Among its predictions was the gravitational redshift, the idea that light climbing out of a gravitational field loses energy, and that this energy loss corresponds to a slowing of time at the source. A clock at the bottom of a tower, according to Einstein's theory, runs slower than a clock at the top, and when light is emitted by the slower clock at the bottom and received by the faster clock at the top, the light arrives with slightly less frequency than it was emitted. It is redshifted, stretched toward the lower end of the spectrum in exact proportion to the difference in gravitational potential between the two clocks. This is elegant. It is precise. It makes a specific numerical prediction, and for 44 years, nobody could test it. The problem was not the theory. The problem was engineering. The gravitational time dilation effect at terrestrial scales is extraordinarily small, over a height difference of 22 meters, which is already a substantial tower. The fractional frequency shift, predicted by general relativity, is approximately 2.5 times 10 to the negative 15th. That is a ratio of about 2.5 parts per quadrillion. To detect this, you need a light source with a spectral line so narrow, so precise, so free from the blurring caused by thermal motion and mechanical recoil, that it can distinguish a frequency shift at that level. In 1915, nothing like that existed. In 1950, nothing like that existed. But by 1958, a German physicist named Rudolf Mossbauer had discovered something that changed the situation entirely. The Mossbauer effect is, at first glance, a technical detail about how atomic nuclei emit gamma rays, but the implications are extraordinary. When a free atom emits a photon, it recoils, the atom kicks backward, and some of the photon's energy is absorbed into that recoil, blurring the frequency of the emitted light across a range far too wide to detect gravitational shifts. Mossbauer discovered that if you embed atoms in a crystal lattice, the entire crystal shares the recoil, and because the crystal is vastly more massive than a single atom, the recoil energy per atom is effectively zero. The gamma rays are emitted with no recoil loss, with a spectral line width so narrow that it can resolve frequency shifts at the level of parts per 10 to the 12th. Sharp enough to hear the difference between two ticking clocks separated by a flight of stairs. Robert Pound, a physics professor at Harvard, read Mossbauer's paper and immediately recognized what it meant. He called it one of the most important experimental developments in physics in years. Within months, he and his graduate student, Glen Rebka, had begun designing the experiment that would either confirm or refute Einstein's 44-year-old prediction about time and gravity. The setup was almost aggressively simple. In the Jefferson Physics Laboratory at Harvard, there was a tower, not an elaborate research facility, just a building with a vertical shaft running from basement to roof. The useful height was 22.5 meters. Pound and Rebka placed a gamma-ray source at the bottom, emitting radiation from iron 57, a nucleus whose Mossbauer line was exceptionally narrow. At the top, they placed a detector, also capable of resonance absorption using the same isotope. The idea was this: if the source at the bottom emits gamma rays that travel up 22.5 meters of gravitational field, and if Einstein is right, those rays should arrive at the detector slightly redshifted, lower in frequency, because time at the bottom is running slower, and a slower clock emits light at a lower rate. The predicted shift was 2.5 times 10 to the negative 15th in fractional frequency. To put that in perspective, imagine a clock that ticks once per second. In 1 second, this clock loses 2.5 quadrillionths of a tick compared to a clock 22 meters higher. That is not a slow clock. That is a clock that is correct to a precision so extreme that to express the error in any practical unit of time would require more decimal places than most calculators can display. There was an additional complication. The thermal vibration of the iron atoms in the crystal broadened the Mossbauer line slightly, adding noise to the measurement. Pound and Rebka solved this with elegant ingenuity. They modulated the source velocity, moving it slowly back and forth using a loudspeaker to sweep the Doppler shift through the predicted gravitational shift, allowing them to use the resonance condition itself as a tuning dial. By finding the velocity at which the moving source's Doppler shift exactly cancelled the gravitational redshift, restoring resonant absorption, they could read off the gravitational shift from the velocity required. The result, published in November of 1959 in the journal Physical Review Letters, was this: the measured fractional frequency shift was 2.57 times 10 to the negative 15th. With an uncertainty of about 10%, Einstein's prediction was 2.45 times 10 to the negative 15th. The agreement was within experimental error, and it was immediately recognized as one of the most precise confirmations of general relativity ever achieved at that point. But here is what I want you to understand about what Pound and Rebka actually measured, because this is where the experiment connects directly to the central question of this entire discussion. They did not measure gravity pulling light down. They did not measure a rocket effect of a photon climbing out of a well. What they measured was the rate at which time flows differently at two heights separated by 22.5 meters. The gamma ray arrived at the top with lower frequency because the source at the bottom was ticking in slower time. A clock at the bottom, if you could see it from the top, would appear to be running slow not because of any mechanical effect, but because the medium in which it operates, time itself, is running at a different rate than the time in which the detector operates. The experiment was not about light, it was about time. The light was just the messenger. This is the thing that tends to get lost in popular accounts of the Pound-Rebka experiment, which are often framed as demonstrations of gravitational redshift in the context of light losing energy. The redshift is real, but the deeper meaning is not about energy. It is about the fact that the tower has a clock at the bottom and a clock at the top, and those clocks do not agree. The universe, at those two heights, is running at detectably different rates, not by some abstract, unmeasurable amount, by a specific, predicted, confirmed, quantified amount. And that amount is exactly what Einstein's equations say it should be, given the height of the tower and the strength of the Earth's gravitational field. In 1964, Pound and his collaborator Joseph Leighton Snyder repeated the experiment with refined technique, improving the accuracy to approximately 1%. The agreement with general relativity held. The tower at Harvard had done something remarkable. It had converted a theoretical prediction about the geometry of spacetime into a tabletop measurement, a number you could write on a piece of paper and check against an equation. This is also the moment in the story where a subtle reframing becomes possible, and I want you to notice it. The gravitational redshift is often described as gravity acting on light, pulling it down, robbing it of energy. But Pound and Rebka showed that you can reframe it entirely in terms of time. The light is not being acted upon by gravity. The light is simply revealing that the clocks at different heights are running at different rates. What looks like gravity-bending light is actually time-bending light. And that reframing from gravity as a force acting on photons to gravity as a consequence of time running unevenly is the conceptual door that everything else in this story walks through. Because if this is what a 22-meter steel tower can tell you, what do you learn when you take the same experiment and scale it up to the size of the planet? Part 3. The clocks that refuse to agree. In October of 1971, two physicists named Joseph Hafele and Richard Keating boarded commercial airplanes carrying atomic clocks. Not metaphorical clocks, not theoretical clocks. Actual cesium beam atomic clocks, the kind that weigh about as much as a carry-on bag and attract a great deal of attention from airport security personnel. They flew east, they flew west, they circumnavigated the Earth, and when they came home and compared their airborne clocks to reference clocks that had stayed on the ground at the United States Naval Observatory, the clocks disagreed. This is one of the most consequential experiments in the history of physics, not because of its technical sophistication it was, by the standards of modern precision measurement, relatively crude, but because of what it proved in the most direct possible terms, that time is not universal, that the path you take through space-time determines how much of it you experience, and that this effect is measurable with clocks you can carry onto an airplane. The experiment involved two competing effects, and this is where it gets interesting, because they work in opposite directions and by different amounts, and the result depends on which one dominates for a given trajectory. The first effect is gravitational time dilation. The airplane is at altitude roughly 10 kilometers above sea level. At that altitude, the gravitational field is weaker than at the surface, meaning the aircraft is less deep in the Earth's gravitational well. Clocks run faster at higher altitude, so the airborne clocks, simply by virtue of being higher up, should accumulate more time than the ground clocks. The second effect is velocity time dilation, which is the time dilation that arises from special relativity. Any clock in motion runs slower than a clock at rest, relative to a given reference frame. The faster you move, the slower your clock runs. The airplane is moving at roughly 800 kilometers per hour. This slows the airborne clock relative to the ground clock. Now, the two effects are in competition, and the winner depends on direction. An airplane flying eastward is moving in the same direction as the Earth's rotation, which adds to its velocity relative to the non-rotating reference frame of space. Eastward flight means greater speed relative to space, which means stronger velocity time dilation, which means the clock runs slower. An airplane flying westward is moving against the Earth's rotation, which subtracts from its total speed relative to space. Westward flight means lower speed relative to space, which means weaker velocity time dilation. So the prediction, combining both effects, the eastward clock, which is moving faster, should lose time overall compared to the ground the velocity effect dominates. The westward clock, which is moving slower against Earth's rotation, should gain time overall compared to the ground the gravitational effect dominates. The results were as follows. The eastward clock lost approximately 59 nanoseconds relative to the ground reference. The predicted loss was 40 nanoseconds, with an experimental uncertainty that made the measurement consistent with the prediction. The westward clock gained approximately 273 nanoseconds relative to the ground. The predicted gain was 275 nanoseconds. The agreement was within a few percent. These clocks do not snap back into agreement when the experiment ends. There is no reset. The accumulated difference is permanent. The eastward clock, when it landed, was genuinely, irreversibly behind the ground clock. Those 59 nanoseconds did not happen for the clock that flew east. They happened for the clock that stayed in Washington, D.C. Time for those two clocks had diverged, and the divergence was real and measurable. What does this mean? It means time is path-dependent. The amount of time you experience, not the amount of time on the clock on the wall, but the amount of time measured by any physical process tied to your position and velocity, depends on the path you take through space-time. Two people who start at the same place and end at the same place do not necessarily experience the same amount of elapsed time between those two events. The difference depends on the curvature of space-time along their respective paths. In the Hafele-Keating experiment, the curvature is created by Earth's gravity, and the paths are airplane flights of different velocity and direction. The result is a permanent, measurable disagreement between clocks that should, in a Newtonian universe, have been in perfect agreement. Now I want to take this idea and bring it somewhere closer to home. Closer, in fact, to wherever you are right now, because the Hafele-Keating result is not just an interesting physics demonstration. It is the operating principle behind one of the most widely used technologies in human history. The Global Positioning System, GPS, is a network of 31 active satellites orbiting the Earth at an altitude of approximately 20,200 kilometers. Each satellite carries atomic clocks, and those clocks are used to broadcast time signals that your phone's GPS receiver uses to calculate your position by comparing the arrival times of signals from multiple satellites. If the clocks on the satellites are not synchronized with clocks on the ground, the position calculations are wrong, and those clocks, by all the laws of physics, cannot be synchronized without accounting for general relativity. Here is what the numbers look like. The GPS satellites are at altitude much higher than Hafele and Keating's airplanes, which means they are in a weaker gravitational field, which means their clocks run faster than ground clocks due to gravitational time dilation. The calculated excess is approximately 45 microseconds per day. A microsecond is 1/1,000,000th of a second, so 45 microseconds is 45 millionths of a second. That sounds tiny. But GPS works by measuring signal travel times, and light travels approximately 300 meters in 1 microsecond. If the satellite clocks are running fast by 45 microseconds per day without correction, the position errors accumulate at a rate of roughly 13 kilometers per day. Your phone would tell you that you are in the middle of a highway when you are standing in your living room. But there is also the velocity effect. The GPS satellites are moving at roughly 14,000 kilometers per hour relative to the ground. That velocity makes their clocks run slow due to special relativistic time dilation by approximately 7 microseconds per day. The two effects are in opposite directions. Gravity makes the satellite clocks run fast, velocity makes them run slow. The net result is a clock that runs fast by approximately 38 microseconds per day. That number, 38 microseconds, is baked into the design of every GPS satellite ever launched. The satellite clocks are deliberately set to tick at a slightly slower rate before launch, so that once in orbit, accounting for both gravitational and velocity corrections, they tick in synchrony with ground clocks. Without this correction, GPS would not work. Every navigation system, every delivery truck, every airplane autopilot, every emergency service, every ride-sharing app, every surveying instrument that uses GPS depends on the corrections predicted by a theory of curved spacetime that Einstein developed in 1915. This is not an abstraction. This is general relativity operating in real time, every second of every day, in a trillion-dollar global infrastructure that humanity has built on top of the assumption that Einstein's description of bent time is correct. And it is correct. It matches. It has always matched. Every test, every satellite, every GPS receiver, every time a map on your phone loads correctly, that is the experimental confirmation of gravitational time dilation running in real time. And if you are sitting with this and finding it slightly unsettling, the idea that the planet beneath your feet is bending time and that this bending has engineering consequences, and that your civilization has quietly engineered around it that feeling is appropriate, because we have not yet talked about how small this effect can get before it disappears. And the answer, as of 2022, is that it does not disappear at human scales. It does not even disappear at the scale of a single millimeter. Part 4, down to the millimeter. There is a particular moment in experimental physics when a phenomenon that was once considered an extreme consequence of exotic conditions, black holes, neutron stars, relativistic flight, becomes a tabletop measurement. We reached that moment for gravitational time dilation in 2022. The experiment was conducted at GLA, the Joint Institute for Laboratory Astrophysics at the University of Colorado Boulder. The research group, led by physicist Jun Ye, had been developing optical lattice clocks based on strontium atoms for over a decade. An optical lattice clock works by trapping atoms in the interference pattern of crossed laser beams, creating a series of nodes where individual atoms sit, each one isolated from its neighbors, each one ticking at the frequency defined by its electronic transitions. In the case of strontium, a transition at 429 terahertz, meaning 429 trillion oscillations per second. This is an extraordinarily stable frequency, and it makes strontium optical lattice clocks among the most precise timekeeping devices ever built. What Junier's group did in 2022 was not just build a precise clock. They built a clock tall enough to measure the gravitational time dilation between its own top and bottom. The clock was a column of about 1,000 strontium atoms, laser-cooled to near absolute zero, arranged vertically in an optical lattice. The column was 1 millimeter tall, 1 millimeter roughly the thickness of a credit card. The atoms at the top of the column were 1 millimeter further from the Earth's center than the atoms at the bottom. And over the course of the measurement, the team was able to resolve the difference in the rate at which time flows at those two heights. The fractional frequency shift they measured was approximately 7.6 times 10 to the negative 21st. Let me give you a sense of what that number means in context. The Rebka experiment in 1959 measured a shift of about 2.5 times 10 to the negative 15th, a shift more than 1 million times larger across a tower 22.5 meters tall. The GLA experiment measured a shift 600 times smaller than Rebka across a distance 22,000 times shorter. That is an improvement in sensitivity of over 10 billion-fold in the intervening 60 years, and it compressed the detectable height difference from the length of a building to the width of a grain of rice. But the GLA result is not just a precision record. It is a conceptual watershed. When gravitational time dilation required a 22-meter tower to detect, it was easy to think of it as something that only matters at architectural scales. When it requires a transatlantic flight, it feels relevant only to aerospace engineering and satellite systems. But when it is measurable across a single millimeter, using a cloud of atoms that fits inside a laboratory rack, it means something different. It means time dilation is not a feature of extreme environments. It is a feature of ordinary objects at ordinary scales in ordinary rooms. Every object that has physical extent, which is every object, exists across a time gradient. A ruler is 100 millimeter ticks long, and across each one of those millimeter ticks, time runs at a slightly different rate. A brick, a book, a human body, all of them span enough height that the gravitational time dilation across their vertical extent is, in principle, the same kind of effect that the Gela experiment measured. Smaller because most objects are denser in one material than strontium clouds are in an optical lattice. But the same physics, the same equations, the same reality, this has not gone unnoticed at the National Institute of Standards and Technology. In work published in 2025, NIST researchers using aluminum-ion clocks, a different atomic species, but similarly extraordinary in precision, demonstrated the ability to resolve height differences of approximately 2 millimeters using gravitational time dilation. Aluminum-ion clocks operate in a different frequency regime than strontium optical lattice clocks, with their own set of systematic advantages, and their precision in this domain represents a complementary confirmation of the same fundamental effect, 2 millimeters. If you hold your index finger and thumb about 2 millimeters apart, you are holding a gap across which the rate of time is measurably different, measurably, not just theoretically, with the best instruments humanity currently possesses. And this matters not just as a statement about the physics, it matters as a statement about what is coming. Clocks of this precision are beginning to enter practical applications in geodesy, the science of measuring the shape of the Earth, because a clock sensitive enough to resolve centimeter-scale height differences can, in principle, map the shape of the gravitational field with extraordinary precision. Instead of using GPS and satellite altimetry to measure variations in sea level and crustal structure, future surveys might use networks of optical clocks, each one reading the local time rate and inferring from it the local gravitational potential, building up a portrait of the Earth's gravitational landscape, centimeter by centimeter. But here is where this connects to the central thread. We started with the observation that your room is not running at one time. We confirmed it with Pound and Rebka's tower. We scaled it up with Haffaley and Keating's airplanes and GPS satellites, and now we have scaled it back down to 1 millimeter and found it again, same effect, same equations, same reality, just smaller. Which means the question that sounded metaphorical when we first asked it is now a statement of tabletop fact. The floor of your room is running in different time than the ceiling, and the difference between the two is the exact same phenomenon that governs how fast time passes near a black hole. The mechanism is identical, only the magnitude changes. And if you can measure time gradients across a millimeter of space, you can ask a question that starts to feel deeply strange. What is happening inside the objects that span those millimeters? What is happening inside a body that stands 1.7 meters tall in a gravitational field? What exactly does it mean for a living system to exist across a gradient in the rate of time? Part 5. The body as a gradient of time. Your body has never existed at a single rate of time. That sounds like a poetic exaggeration until you strip it down to what general relativity actually says, and then it becomes something more unsettling, a precise, unavoidable consequence of living inside a gravitational field. There is no metaphor hiding here, no philosophical flourish required to make it true. It follows directly from the same framework that powers GPS corrections, predicts black hole behavior, and has passed every experimental test we've been able to throw at it since the middle of the 20th century. The uncomfortable part is not that it might be wrong. The uncomfortable part is that it is right, and it applies to you in this exact moment, down to the position of your bones in space. To understand what that means in practice, it helps to slow the idea down and make it almost annoyingly concrete. Your body is not a point. It is a vertical structure extending roughly from the floor to about 1.5 to 2 meters above it when you are standing. That difference in height is not just spatial separation. It is separation inside a gravitational gradient. And in Einstein's description of gravity, that gradient is also a gradient in the rate at which time itself passes. Near the surface of the Earth, the effect is small, but not negligible. Clocks lower in a gravitational field tick more slowly than clocks higher up. This is not speculative. It has been directly measured. The fractional difference is tiny, on the order of about 2 parts in 10 quadrillion per meter of height difference. But tiny in physics does not mean irrelevant. It means cumulative, consistent, and measurable if you have the right instruments. So if your head is roughly 1.7 meters above your feet, then your body spans a measurable time differential. Over the course of a human lifetime, that difference accumulates into something on the order of hundreds of picoseconds, roughly a few hundred trillionths of a second between the bottom of you and the top of you. Not enough to affect biology, not enough to notice, but enough to exist in the equations, and enough to be confirmed indirectly by the same physics that has been tested in satellites and precision atomic clocks. That is the first unsettling realization. Even inside a single body, time is not uniform. And the moment you accept that, the scale begins to stretch. Move from your body to geography. Altitude becomes the next natural experiment. If you live at higher elevation, you sit slightly higher in Earth's gravitational field. That means your local time runs slightly faster compared to sea level. The effect is still small microseconds over a lifetime, but now it is no longer theoretical. It becomes something that engineers must account for when synchronizing systems across different elevations. A person living at 5,000 meters above sea level, somewhere in the Andes or Himalayas, experiences a slightly weaker gravitational field than someone at sea level. Over an entire life, that translates into a difference of roughly 1 to 2 microseconds. Again, this does not affect aging in any meaningful biological sense. But it does mean something subtle and important. Where you live on Earth slightly changes how quickly your life is counted by physics. And that is where intuition starts to fracture, because altitude stops being just geography. It becomes a way of moving through time at different rates. At sea level, time runs a little slower. At higher elevation, a little faster. Not metaphorically, literally, measurably. The Earth is not just a place you inhabit, it is a structure that defines your rate of temporal flow. Now extend that thought further outward. The Earth itself is deep inside the gravitational well of the Sunday. The Sun is inside the gravitational environment of the Milky Way galaxy. And the galaxy sits inside a larger cosmological space-time that is itself expanding. Each layer contributes to how time is experienced locally. When you compare a clock on Earth to a hypothetical clock far away in deep interstellar space, far from stars, planets, and gravitational wells, the Earth-bound clock accumulates less proper time over long durations. In practical terms, the difference is small over a human lifetime. Depending on how you model the contributions of solar, galactic, and local gravitational fields, the Earth-bound life of a human being might accumulate something like 1 to 2 seconds less proper time compared to an identical life spent far away from gravitational sources. 1 or 2 seconds does not sound like much, but the meaning is not in the magnitude. The meaning is in the principle. The mass of the Earth and the Sun has literally reduced the total amount of time you experience. That leads to a subtle but important shift in perspective. Gravity is not just something that determines where objects fall. It determines how much time those objects get to experience while they exist in a gravitational field. The planet beneath your feet is not just supporting your body. It is also shaping the rate at which your existence unfolds. And once you see that, the room you are in stops being a simple geometric space. Let us return to that room. It is easy to think of it as stable, neutral, and uniform. A floor, a ceiling, four walls, a static container for events. But physics does not describe it that way. Every point in that room sits at a slightly different gravitational potential. That means every point has a slightly different rate of time associated with it. The floor is deeper in the gravitational well than the ceiling. Your feet are deeper than your head. Even the air in the room has a gradient in time rate, however small. So the room is not uniform. It is stratified in time. This is where the idea becomes difficult to visualize, because we are used to thinking of time as something that flows uniformly everywhere, like a background parameter. But general relativity replaces that picture with something more geometric. Time is not a universal river. It is part of a structure that can be curved, stretched, and tilted depending on mass and energy. And the floor of your room is literally deeper in that curvature than the ceiling. So when you stand up, you are not just changing position in space, you are changing position in time rate. Now, zoom back into your body again, because this is where the idea becomes almost intimate. Every biological process you experience, cell division, neural firing, protein synthesis, is happening across a body that is internally out of sync in a relativistic sense. The differences are absurdly small, but they are not zero. The atoms in your feet are, over your lifetime, experiencing slightly less elapsed proper time than the atoms in your head. Your brain is not running on a different clock in any functional sense. But physically, the space-time region it occupies is not identical to the one occupied by your lower body. There is no moment where your body becomes desynchronized in any noticeable way, because every process inside you is also local to its own space-time region. Chemistry, biology, and neural activity all operate within the same relativistic framework, but the deeper statement remains. There is no single, universal time coordinate being shared by every part of you. There are only local times stitched together by the geometry of space-time. This leads to a conclusion that sounds simple, but carries enormous conceptual weight. You are not located in time the way you are located in space. You are distributed across it. And that brings us to the deeper question hidden underneath all of this. We can measure how time changes. We can predict it. We can correct for it in engineering systems. We can confirm it with experiments from the smallest laboratory setups to satellite networks orbiting Earth. But none of that tells us what time actually is. That question is where physics stops being purely descriptive and starts becoming interpretive. One possibility is that time is a real physical entity, something like a flowing medium that can be stretched and slowed by gravity. In that picture, gravity acts as a kind of deformation of a pre-existing temporal substance. But this raises immediate problems. What is that substance made of? What does it mean for it to flow at different rates in different places? And why would that flow obey the specific mathematical structure that general relativity predicts so precisely? A second possibility is more conservative. Time is not a thing at all, but a coordinate in a geometric structure called space-time. In this view, asking what time is made of is like asking what a coordinate system is made of. There is no substance underneath it. There is only geometry. Gravity does not bend time as an object. It defines the shape of space-time, and time is simply one direction in that shape. The curvature we measure is not a deformation of a medium. It is the structure itself. A third possibility goes even deeper and becomes far more speculative. In approaches to quantum gravity, time may not exist fundamentally at all. Instead, it may emerge from more basic relationships, entanglement, information flow, or correlations between quantum states. In this view, what we call time dilation is not the slowing of a fundamental entity, but a macroscopic reflection of how underlying quantum relationships are organized in the presence of mass and energy. These interpretations are not just philosophical variations. They are mathematically consistent ways of reading the same equations. And crucially, they all agree with every experiment we currently know how to perform. Pound Rebka, GPS satellites, atomic clock comparisons, high-altitude measurements, and millimeter-scale laboratory tests all confirm the same quantitative structure, but they do not distinguish between what time fundamentally is. That is the strange boundary we are standing on. We can measure how time behaves with extreme precision, but we cannot yet say what it is in the deepest sense that produces that behavior. We know how it bends, but not what is bending in the most fundamental ontology of the universe. So when you return to the simplest possible observation standing in a room, feeling the weight of your body against the floor, it stops being simple. That sensation of weight is not just a force. It is the experience of being held within a gradient of space-time. It is the local signature of a deeper structure in which time itself is not uniform. Gravity, then, may not be something acting on you from the outside. It may be the geometry of the environment in which your existence is unfolding. The floor is not pulling you down. It is sitting deeper in a region where time runs differently, and your body follows the structure defined by that difference. And that leaves us with the most important unresolved idea of all. We know how time changes with position in a gravitational field, but we do not yet know what time is such that it can change at all. That question is still open, not because physics has failed, but because it has pushed as far as it currently can. Beyond this point lies a deeper layer of reality. We have not yet fully accessed a layer where time is either fundamental, geometric, or emergent, and we do not yet know which description is the final one. Until then, every clock continues to tick in its own local frame. Every object continues to fall along the gradients of space-time, and you continue to live your life inside a structure where even the distance between your head and your feet is, in a very real sense, a difference in time. Part 6. The reversal. Gravity is time. Here is a statement that should stop you for a moment. Nothing in the universe is at rest. Everything is moving through space-time at the speed of light. This is not poetry. This is a consequence of special relativity. In space-time, the four-dimensional structure that combines the three dimensions of space with time, every object moves at the same total rate, the speed of light, all the time. What varies is how that motion is distributed between the spatial and temporal dimensions. An object that is stationary in space is moving entirely through time at the speed of light. An object moving through space at close to the speed of light is moving through time very slowly. The faster you move through space, the slower you move through time, and the trade-off is always exact. Always total speed equals the speed of light. What does this have to do with gravity? John Archibald Wheeler, one of the great physicists of the 20th century, and the man who coined the term black hole, had a way of describing general relativity that cuts to the core of what gravity actually is. Wheeler put it this way: space-time tells matter how to move, and matter tells space-time how to curve. But you can unpack that further. When matter curves space-time, one of the things it curves is the time component of that space-time. Near a mass, time runs slower. And when time runs slower in one location than another, objects moving through space-time respond to that gradient. Here is the key claim. An object near a massive body falls not because a force is pulling it, but because the geometry of space-time near that body is curved in such a way that the direction of maximum proper time, the direction in which time flows most richly, is toward the mass. And objects in space-time naturally follow paths, called geodesics that maximize their accumulated proper time. On a flat surface, a geodesic is a straight line. On a curved surface, like the surface of the Earth, or the curved space-time near a massive body, a geodesic is a curved path. And the geodesics of space-time near a mass curve toward the mass, because time near the mass is running slower. And the way to maximize proper time in a system where time is running at different rates is to move toward the region where time is densest. This is the central reversal at the heart of general relativity, and it is what I want you to understand as clearly as possible. Falling is not a response to a force. Falling is what happens when you follow time. Falling is the path that maximizes the proper time you accumulate on your journey through space-time. It looks like acceleration because the geometry of space-time near the Earth is curved, and curved geometry produces paths that, when projected into our ordinary three-dimensional perception, look like objects accelerating downward. But the objects are not being pulled. They are following the natural flow of curved space-time, the same way a straight path on the surface of the Earth eventually curves if you draw it long enough, not because you were pushed sideways, but because the surface itself is curved. Let me try a different angle. Imagine standing at the surface of the Earth, looking at an object hovering above you. That object is not accelerating relative to the Earth, but you are. You are being continuously accelerated upward by the ground beneath your feet. That acceleration, the one you feel as your weight, is not you being pulled down by gravity. It is you being pushed up by the ground, away from the geodesic that you would naturally follow if nothing were impeding you. If the ground were removed and you were in freefall, you would be weightless, you would feel no force, you would be following the natural curved path of space-time, which happens to be aimed at the center of the Earth. Weight is not the feeling of gravity, weight is the feeling of being held off the natural path of space-time, the path that follows the time gradient. This reframing is not just philosophical, it is mathematically precise. The geodesic equation of general relativity, the equation that describes how an object moves through curved space-time, does not contain any force term. There is no pull, there is no push. There is geometry, and there are paths that objects follow through that geometry, and those paths curve the way they do because time is running at different rates in different locations. And the mathematical structure of space-time in the presence of mass ensures that the direction of falling is the direction of slower time. Here is the part that connects everything we have discussed so far. The Rebka experiment showed that time runs slower at the bottom of the tower than at the top. The GPS satellites show that time runs slower on the ground than in orbit. The Glen strontium clock showed that time runs slower at the bottom of a 1 mm column than at the top. In each case, the direction of slower time is the same as the direction of gravitational acceleration, downward, toward the center of the Earth. And the magnitude of the time rate difference at each location matches the magnitude of the gravitational field at that location. These are not two separate facts, they are the same fact. The time gradient and the gravitational gradient are the same thing, expressed in different languages. There is an analogy from optics that helps make this concrete. Light traveling through a medium bends when the speed of light in that medium is not uniform. This is the phenomenon behind lenses, mirages, and the bending of light near the Earth's surface in hot weather. The light bends toward the region of lower speed because the wavefront on the slow side is moving more slowly, and the wavefront curves as a result. Gravity near a mass does the same thing to everything moving through space-time. Near a mass, the effective speed at which things move through time is lower. The wavefronts of everything light, matter, probability amplitudes, causal influence curve toward the slower region, toward the mass, toward the center of the gravitational field. The falling of an apple is, in this picture, the same phenomenon as the bending of a light ray near the sunday. Both are wavefronts curving towards slower time. And, here is the thing, at the scale of the Earth's surface, the vast majority of the space-time curvature is in the time component, not the spatial component. The spatial curvature of space-time near the Earth is measurable, but small. Its effects are detectable only in very precise measurements. The time curvature, by contrast, is responsible for essentially all of the gravitational acceleration you feel when you stand up and feel your weight. The 1g you experience, the 9.8 meters per second squared of gravitational acceleration at the Earth's surface, is almost entirely a consequence of time running slower, closer to the ground. It is not space that is bent, it is time. And the thing we call gravity, the weight, the fall, the orbit, is what the bending of time looks like when you are living inside it. This is the central claim. This is what the entire experimental spine we have walked, from Pound and Rebka's tower to the GPS network to the Gila millimeter measurement, was testing. And it passes every test. Gravity is not a force acting on objects in a flat arena of space. Gravity is the gradient of time, and everything that falls is following the direction in which time runs slowest. But this naturally raises a question that the physics has so far not fully answered. If gravity is the gradient of time, what happens when that gradient becomes extreme? What happens when the slowing of time is not a fractional effect of parts per quadrillion, but something that approaches and reaches a complete stop? Part 7. The equation that predicts frozen time. In 1916, the German physicist Karl Schwarzschild solved Einstein's field equations for the simplest possible case, a single, perfectly spherical, non-rotating mass in an otherwise empty universe. He sent his solution to Einstein from the Russian front, where he was serving as an artillery officer during the First World War. He died of illness a few months later, without knowing that the solution he had derived would eventually describe one of the most exotic structures in the known universe. It is called the Schwarzschild metric, and embedded in it is an equation that predicts explicitly and precisely how gravity slows time and how, in the limit, time can be slowed to a complete stop. The key formula in the Schwarzschild metric for time dilation is the following. For an observer stationary at a given distance r from the center of a mass, the relationship between their proper time, the time they actually experience, and the coordinate time of a distant observer is given by the square root of the quantity 1 minus the Schwarzschild radius divided by r. The Schwarzschild radius, denoted r sub s, is a specific distance associated with a given mass. It is equal to 2 times the gravitational constant times the mass divided by the square of the speed of light. For the Earth, the Schwarzschild radius is about 9 millimeters, roughly the size of a marble. For the Sun, it is about 3 kilometers. For a stellar black hole 10 times the mass of the Sun, it is about 30 kilometers. Let us walk through what this formula tells us. Far from the mass, when r is very large compared to r sub s, the ratio r sub s divided by r is nearly 0, and the square root is nearly 1. The proper time and the coordinate time are nearly equal. Distant observers and distant objects tick at almost the same rate. This is the situation we are in right now, sitting on the surface of a planet whose Schwarzschild radius is 9 millimeters, while we sit 6,371,000 meters above the center of that planet. The effect is tiny, about 10 to the negative 10th in fractional terms, and the clocks are nearly in agreement, but not exactly. Now move closer to the mass, but still outside the Schwarzschild radius. As r decreases toward r sub s, the ratio r sub s divided by r approaches 1, and 1 minus r sub s over r approaches 0. The square root of something approaching 0 approaches 0, which means the proper time measured by a stationary observer at radius r approaches 0 relative to the coordinate time of the distant observer. Their clock is running slower and slower. At a neutron star, which might have a radius of 10 kilometers and a mass of 1.4 to 2 times the mass of the Sun, giving it a Schwarzschild radius of approximately 4 to 6 kilometers. The ratio r sub s over r is on the order of 0.3 to 0.6, and the time dilation factor is roughly 0.6 to 0.8. A clock on the surface of a neutron star runs at 60 to 80% of the rate of a clock in deep space. That is not a small effect. That is a clock running at most of 1 normal second for every 1.5 seconds of deep space time. These numbers are not hypothetical. Neutron stars are real objects. There are thousands of known neutron stars in the Milky Way, and we can observe their pulsations, their emission spectra, and in some cases their gravitational lensing. The time dilation factor at their surfaces has direct observable consequences for the light they emit and the timing of their pulsations. And then there is the extreme limit. As r approaches r sub s, the time dilation factor approaches 0. The clock at the Schwarzschild radius runs infinitely slowly relative to a distant observer. It does not tick. Its time rate, from the perspective of the outside universe, is 0. This is what the equation says, and it says it without ambiguity. At the Schwarzschild radius of a sufficiently massive object, time stops. Not metaphorically, not approximately. The proper time of a stationary observer at r equals r sub s would be 0 relative to all the time in the rest of the universe. Now, I want you to notice something about this, because it is easy to treat the Schwarzschild radius as a distant abstraction, something that only applies to exotic objects far from everyday experience. But the Schwarzschild metric is not limited to black holes. It describes the exterior gravitational field of any spherically symmetric mass, including the Earth, the Sun, every planet and star in the sky. The same formula that says time runs 10 to the negative 10th slower on the Earth's surface, which is what your GPS satellites correct for, is the same formula that says time runs infinitely slowly at the Schwarzschild radius of a black hole. The mechanism is the same. The equation is the same. Only the magnitude changes, scaling continuously from the barely detectable gradient in the room where you are sitting to the absolute frozen boundary of a collapsed star. Gravity is not multiple phenomena. It is one phenomenon. Time running at different rates in different places. The tower at Harvard, the airplane flights around the world, the GPS satellites, the millimeter-scale strontium clock, and the event horizon of a black hole are all on the same continuum. They are all the same effect, occurring at different points on a scale that runs from invisible to infinite. Part 8. The edge where time stops. Imagine you are watching a clock fall toward a black hole. You are stationary, far away, watching through a telescope. What do you see? At first, the clock is falling. Normally you can see it accelerating, its face still legible. But as it falls deeper into the gravitational field, something begins to happen to the light it emits. The light has to climb out of a deepening gravitational well to reach you. And, as we now know, that climb costs frequency. The light is redshifted. The clock, as observed from your position, begins to run slower. Its hands, if it has hands, begin to decelerate. The rate of ticking decreases. The light from the clock becomes redder, then redder still, dimmer and dimmer, as the photons lose more and more energy fighting the gravitational field on their way out. And then, as the clock approaches the Schwarzschild radius, the event horizon, something complete happens. The clock, from your perspective, does not cross the horizon. It slows asymptotically. Its ticking rate, as you observe it, approaches 0. The light it emits is redshifted toward infinitely long wavelengths, fading to invisibility. From your perspective, the clock freezes at the horizon, its last image infinitely redshifted, its time apparently stopped. It never, in your observable universe, crosses the horizon. The last photon you ever receive from it was emitted just before the crossing, and that photon is shifted to nearly infinite wavelength, nearly zero energy, and arrives after a delay that, formally, is infinite. This is the external observer's experience of a clock falling into a black hole. The clock slows, reddens, and freezes, trapped forever at the edge of the horizon, its time rate approaching zero as the event horizon's time dilation approaches infinity. The clock is the extreme limit of every phenomenon we have been discussing throughout this entire conversation. The Rebka experiment measured a time ratio of 1 minus a few parts in 10 to the 15th. The GPS correction is parts in 10 to the 10. The neutron star surface is a factor of 0.6 or so. The event horizon is zero. These are not different phenomena. They are the same phenomenon at different points on the scale. But here is a critical distinction that is worth introducing carefully, because it is one of the places where the popular understanding of black holes diverges most sharply from the actual physics. The external observer sees the clock slow and freeze. The external observer never, within any finite time, sees the clock cross the horizon. But this is a statement about the external observer's reference frame about coordinate time, the time assigned to events by a distant observer with a particular choice of coordinates. It is not a statement about the clock's own experience. The clock, falling freely toward the event horizon, is in freefall. It is following a geodesic, which means it feels no force, no weight, no stretching or compression at the horizon for a large enough black hole. From the clock's own perspective, its own proper time, it crosses the horizon at a finite, calculable time after it begins falling. There is no physical barrier at the horizon, no wall, no sign. The clock or the astronaut, or whatever falls in, does not experience a dramatic event at the crossing. The event horizon is not a surface in any physical sense. It is a surface of no return, defined by the global causal structure of spacetime, a location from which no future directed path through spacetime can ever reach the outside universe. It is a consequence of the geometry of spacetime, and that geometry, at the horizon itself, is locally flat, locally normal. The astronaut crossing it would feel nothing special. So you have two apparently contradictory statements. From the outside, the clock never crosses. From the inside, it crosses in finite time. Both are correct. They are not contradictory because they refer to different observers making measurements in different reference frames, and in general relativity, there is no single correct frame. There is no external view that overrides the infalling view. There is no infalling view that overrides the external view. Both are valid descriptions of the physics from their respective positions in the time gradient. This observer dependence is itself a consequence of the central phenomenon we have been discussing. The external observer and the infalling clock are at different positions in an extreme time gradient. Their time rates are different, not slightly different, as in the Rebka tower, but dramatically different, divergently different, as the horizon approaches. The disagreement between them about when events happen, whether the horizon is crossed, when the clock reaches it, what the sequence of events is a direct consequence of the fact that they are separated by an infinite gradient in the rate of time. The same mechanism that makes the floor of your room run slower than the ceiling makes the event horizon of a black hole appear, to an outside observer, to freeze all infalling clocks at the moment of crossing. And if you ask what lies beyond the horizon, what happens if you follow the infalling clock through, the answer involves one of the strangest consequences of general relativity, a consequence that turns everything you thought you understood about the direction of time inside out. Part 9. Inside. Time becomes direction. When you fall through the event horizon of a black hole, according to the mathematics of the Schwarzschild metric and its interior solution, something happens to the coordinates of spacetime that has no analogue in any other situation in the physical universe. The coordinate that was previously the time-like coordinate, the one that points in the direction of increasing time, and the coordinate that was the radial spatial coordinate, the one pointing toward or away from, singularity exchange their character. Inside the event horizon, the radial coordinate becomes time-like. The time coordinate becomes space-like. Let me be precise about what this means, because it is very easy to make this sound more mystical than it is, and it is also easy to make it sound less significant than it actually is. In general relativity, the difference between a time-like direction and a space-like direction is not a matter of labeling or convention. It is physical. It is real. It has consequences for what is possible. A time-like direction is one you can move along, but cannot choose to reverse. You cannot stop moving through time. You cannot choose to go backward in time. You move through the time-like dimension at whatever rate your proper time dictates, and that rate may vary depending on your position in a gravitational field or your velocity through space. But the direction never changes. Forward only, always. A space-like direction, by contrast, is one you can choose. You can move left or right. You can stop moving east and start moving west. You can sit still in the x direction entirely. Space is optional. You can negotiate with space. Time is not optional, and you cannot negotiate with it. This distinction matters enormously for what happens inside a black hole. Inside the event horizon, past the boundary from which no signal and no object can ever return to the outside universe, the radial direction, the direction that, outside the horizon, pointed toward and away from the singularity at the center, becomes time-like. This is not a coordinate glitch. It is not an artifact of a poorly chosen reference frame. It is a statement about the causal structure of space-time in that region, and it means something physically precise. The direction toward the singularity is no longer a spatial direction you can choose to move in or avoid. It is a temporal direction. It is the future. And just as you cannot choose to move backward in time on the outside of a black hole, you cannot choose to move away from the singularity on the inside. The singularity is not a place, it is a moment. It is the future moment that awaits every infalling object, as inevitable and as unreachable in reverse as tomorrow morning is for you right now. The analogy here is worth sitting with, because I think it is one of the most clarifying things you can say about what a black hole actually is. On the outside, the singularity is a location in space. Spatial locations are negotiable. You can point a rocket engine at them and choose not to be there. You can orbit at a safe distance. You can, with enough thrust and enough fuel, increase the distance between yourself and the singularity indefinitely. The singularity is dangerous, but it is avoidable. For the same reason, any place in space is avoidable, because space gives you options. Inside the event horizon, that changes completely. The singularity is no longer a place you can choose to avoid. It is a moment you are already moving toward, as surely and as unstoppably as you are moving toward next Wednesday. You cannot fire a rocket and escape the future. The future is not a location in space that you can steer around. It is the direction time is pointing, and time, inside the horizon, is pointing inward, toward the singularity. Without exception, how long does it take? The answer depends entirely on the mass of the black hole, because the size of the event horizon scales directly with mass, and the proper time available inside scales with the size of the horizon. For a stellar black hole, one with a mass of roughly 10 times the mass of the Sun, which is toward the smaller end of the known black hole population, the Schwarzschild radius is approximately 30 kilometers. Once inside the horizon, an infalling object has a maximum proper time before reaching the singularity that can be calculated precisely from the Schwarzschild geometry. The formula gives roughly pi times the Schwarzschild radius divided by twice the speed of light. For a 10 solar mass black hole, that works out to on the order of 150 microseconds, a fraction of a millisecond. From the moment of crossing the horizon to the moment of reaching the singularity, less time passes than it takes to blink. Now, scale up. For a supermassive black hole, the kind that sits at the center of a large galaxy, with a mass of perhaps 1 billion solar masses, the Schwarzschild radius balloons to roughly 2.5 billion kilometers, larger than the orbit of Uranus, larger than anything in our solar system except the Sun itself and the outer reaches of the heliosphere. At that scale, the proper time inside the horizon is on the order of minutes to hours. An astronaut falling into a supermassive black hole would not be immediately destroyed at the horizon. The tidal forces there are actually gentler than they are at a stellar black hole's horizon, because the gradient is spread over a much larger distance, and they would have time, measured in their own proper experience, to observe their surroundings, think, and eventually meet the singularity. Neither of these scenarios involves anything that feels like what we normally imagine when we picture falling into a black hole. There is no wall, there is no barrier. At the event horizon, locally, space-time is smooth. An infalling observer in freefall feels nothing special at the crossing. There is no alarm. No dramatic physical event marks the moment of entry. The horizon is not a surface in the way a planet's surface is a surface. It is a boundary defined by the global causal structure of space-time, a point of no return determined by the geometry of the region, not by any local physical feature. What marks it is not what you feel. What marks it is what becomes impossible. Before the crossing, you had options. You could, in principle, accelerate and escape. After the crossing, the option is gone not because you lack the fuel or the technology, but because the geometry of space-time in that region has been reorganized so completely that the concept of moving away from the singularity has stopped being a spatial concept and become a temporal one. It is as geometrically impossible to move away from the singularity inside the horizon as it is to move backward in time outside it. The physics forbids it at the level of the structure of space-time itself. This is the ultimate expression, the absolute turned up to maximum endpoint of the phenomenon that runs through this entire story from the beginning. Time running at different rates in different places, time being shaped by the presence of mass. Time being not a neutral backdrop against which events happen, but a geometric quantity, a component of the structure of space-time that responds to mass and energy and determines the paths that everything in the universe is allowed to follow. The gradient in your room is gentle, a few parts in 10 to the 14th between floor and ceiling, barely measurable even with the best instruments ever built. And yet it is the same gradient, the same mechanism, the same equation, the same physical phenomenon that at the event horizon becomes so extreme that time stops entirely from the perspective of an outside observer, and inside the horizon reorganizes the geometry of space-time so completely that what was a direction in space becomes the direction of the future. The thing that makes apples fall and makes GPS satellites need corrections and made Robert Pound send gamma rays up a 22-meter tower in Cambridge, Massachusetts in 1959 has, taken to its logical conclusion, produced a region of the universe where the distinction between future time and inward space has been eliminated, where the singularity is not a place but a moment, where the future is not a direction in time but a direction in what used to be space. No other situation in the known universe does this. No other configuration of space-time, no other extreme environment, no other physical scenario produces this particular inside-out rearrangement of the time-like and space-like directions. It is unique. It is a direct consequence of taking the mild, barely perceptible time gradient in the room you are sitting in right now and scaling the underlying mass until the equations reach their limit. And all of that, every experiment, every measurement, every satellite correction, every gamma ray climbing a tower, every strontium atom in a millimeter-tall cloud, ticking at a rate determined by its height. All of it tells us with extraordinary precision how gravity bends time. What none of it tells us is why. What time actually is, at the level where a planet can alter its rate. Whether time is a real, independent thing that mass deforms the way a weight deforms a rubber sheet. Whether it is simply an aspect of geometry, with no underlying substance to deform, just shape, all the way down, or whether it emerges from something more fundamental, something we haven't fully described yet, something at the quantum level where the deepest structure of reality operates, by rules we are still working out. We have measured the bending with extraordinary precision. We have confirmed it across scales from millimeters to megaparsecs. We have built the correction into the infrastructure of civilization. And we still cannot tell you, with any confidence, what is being bent. That question is open, genuinely, uncomfortably, fascinatingly open. And it has been open since the morning a clerk in a Swiss patent office picked up a pen and started writing down the theory that would eventually lead us here to the floor of a room running in slower time than the ceiling, to the event horizon where time stops, and to the singularity that is not a place, but a moment, waiting in the direction the future is pointing. Part 10. 3 interpretations, 1 reality. Here is the strange, almost uncomfortable position physics has arrived at. For more than a century, we have been building a case, not a speculative one, not a philosophical one, a hard, experimental case. In 1959, Robert Pound and Glen Rebka stood inside a tower at Harvard and measured a shift so small it bordered on absurd, a change in frequency on the order of parts in a quadrillion. And yet it was there, exactly where Albert Einstein said it would be. Light climbing upward through Earth's gravity lost energy, not because anything was pushing on it, but because time itself was running differently at the top than at the bottom. That was the first crack. Since then, the evidence has not just accumulated, it has converged. Atomic clocks flown around the Earth refuse to stay synchronized. Satellites in orbit around the planet, forming the backbone of the global positioning system, tick faster than clocks on the ground by tens of microseconds every day, and must be corrected continuously or navigation collapses. More recently, laboratories have pushed this effect down to the smallest scales ever tested. At Glen, researchers measured gravitational time dilation across a vertical separation of just 1 millimeter, a distance smaller than the thickness of a fingernail. The difference was unimaginably tiny, but it was real, repeatable, and exactly what the equations predicted. Every time we have asked the universe whether gravity bends time, it has answered yes. The predictions work. The mathematics is internally consistent. The experiments agree across decades, technologies, and scales, from towers to airplanes to satellites to quantum clocks. There is no serious dispute about any of this. In the language of science, gravitational time dilation is not just supported, it is overdetermined. It has been confirmed so many different ways that the possibility of it being wrong has effectively vanished. And yet, in the middle of all this agreement, something unexpected remains. Physicists still argue about what it means. This is not a failure of the theory. It is not a sign that something is broken. In fact, it is a pattern that has appeared before. The history of quantum mechanics is, in many ways, a century-long conversation among scientists who all agree on the equations, all agree on the predictions, and all agree on how to use them, and yet disagree, sometimes profoundly, on what those equations are telling us about reality. The mathematics works perfectly. The interpretations do not converge. The same situation exists here. In the physics of gravity and time, general relativity is one of the most successful theories ever constructed. It predicts gravitational time dilation with extraordinary accuracy. It describes black holes, gravitational waves, and the expansion of the universe. It has passed every experimental test we have been able to devise. But when we ask a deeper question what gravity actually is, at the most fundamental level, the answers begin to split. There are, broadly speaking, three distinct ways to interpret what all of these experiments are telling us. Three ways to understand what it means for gravity to bend time. And what makes this situation so unusual is that all three interpretations are consistent with every piece of evidence we have. They are not different theories. They are different realities, layered on top of the same mathematics. The first interpretation is the most direct, and in some ways the most intuitive once you accept the premise. It takes the experimental results at face value and pushes them to their logical conclusion. Gravity is a gradient of time. In this view, mass does not pull objects in the way Newton imagined. Instead, mass alters the rate at which time passes from place to place. The presence of the Earth, or the Sun, or any massive object creates a landscape in which time flows unevenly slower, closer to the mass, faster, further away. Objects moving through this landscape follow paths that are shaped by these differences. What we perceive as falling is simply motion along the natural curves defined by that time gradient. Put differently, objects move toward regions where time runs more slowly, not because they are being dragged there by a force, but because that is the straightest possible path through the geometry of space-time. In the same way that light bends when it enters a medium where it travels more slowly, matter bends when it enters a region where time itself runs more slowly. From this perspective, gravity is not something acting on time. Gravity is time behaving unevenly. This interpretation has a kind of elegance to it. It explains why gravitational time dilation is not just a side effect, but a central feature of the phenomenon. It aligns with the idea, often associated with John Archibald Wheeler, that matter tells space-time how to curve, and space-time tells matter how to move. And in practical terms, it matches what we actually measure. The gravitational field at the surface of the Earth is dominated not by spatial curvature, but by temporal curvature, the variation in the rate of time. The weight you feel standing on the ground can be understood in this framework as the result of being prevented from following the natural path that time is guiding you along. It is a powerful idea, but it is not the only one. The second interpretation takes a step back and questions the language itself. It suggests that the phrase "gravity bends time" might be subtly misleading, not because it is incorrect, but because it implies a separation that may not exist. In this view, there is no independent entity called time that exists on its own and then gets bent by gravity. Instead, there is only space-time, a unified, four-dimensional structure with geometric properties. Time is not something separate from that structure, it is one aspect of it. Specifically, it is the dimension along which cause and effect unfold. From this perspective, asking what gravity does to time is a bit like asking what a map does to the roads it represents. The roads are not separate from the map. The map is the roads expressed in a particular form. Similarly, space-time is not a stage on which time and space exist independently. It is the combined structure that defines both. Gravity, then, is not bending time as an external substance. It is shaping the geometry of space-time itself. And what we experience as time dilation is simply one manifestation of that geometry, one component of a larger, unified structure. This interpretation does not contradict the first. It reframes it. It shifts the emphasis from time as a thing being acted upon to geometry as the underlying reality. It removes the need to imagine a river of time that flows and gets distorted, and replaces it with a more abstract, but arguably more precise picture. A geometric structure in which distances and durations are defined by the same underlying rules. And yet, even this may not be the deepest layer. The third interpretation pushes further. into territory that is still being actively explored. It begins with a provocative idea. What if time is not fundamental at all? In many approaches to quantum gravity, the attempt to reconcile general relativity with quantum mechanics time does not appear in the fundamental equations. The most famous example is the Wheeler-DeWitt equation, which describes the quantum state of the universe without referencing time in any explicit way. It is an equation that governs the entire cosmos, and yet it contains no variable corresponding to time. If this is correct, it suggests something remarkable. Time is not built into the foundation of reality. It is not a basic ingredient like mass or charge. Instead, it emerges from something deeper. The question then becomes, emerges from what? One of the most intriguing answers comes from modern theoretical work on quantum entanglement and space-time geometry. In 2013, Juan Maldacena and Leonard Susskind proposed a conjecture known as ER equals EPR. The idea is deceptively simple, but its implications are profound. ER refers to Einstein-Rosen bridges, mathematical structures that connect distant regions of spacetime, often described as wormholes. EPR refers to Einstein-Podolsky-Rosen pairs quantum systems that are entangled, meaning their properties are correlated no matter how far apart they are. The conjecture suggests that these two phenomena are not just related, but fundamentally the same. That the connectivity of spacetime, the fact that two regions are linked by geometry, is equivalent to the entanglement between their underlying quantum states. If this is true, then spacetime itself, including its temporal structure, is not fundamental. It is built out of patterns of entanglement. The geometry we observe is a large-scale manifestation of microscopic quantum relationships. And if spacetime is emergent in this way, then gravitational time dilation, the slowing of clocks in a gravitational field, is not the bending of an independent dimension. It is a reflection of how those underlying correlations are arranged. Time flows differently in different regions because the quantum structure of those regions is different. Gravity, in this picture, is not a force, and not even a geometric curvature in the traditional sense. It is a property of how information is organized in the universe. What makes this situation so striking is not just the diversity of interpretations, but the fact that they all agree on what we can measure. The experiments we began with the tower at Harvard, the atomic clocks on airplanes, the satellites orbiting Earth, the millimeter-scale measurements in quantum labs are all explained equally well by all three perspectives. The equations do not change. The predictions do not change. Only the story we tell ourselves about what those equations mean changes. And so we find ourselves in a position that is both stable and uncertain. Stable because the physics works. Uncertain because the meaning is still open. When we ask what gravity does to time, we can answer with confidence. It changes the rate at which time passes. We can quantify that change to extraordinary precision. We can build technologies that depend on it. We can trace its effects from the smallest laboratory experiments to the largest structures in the universe. But when we ask what time is what kind of thing it must be for gravity to affect it in this way, the answers diverge. It might be a real, fundamental dimension that can be stretched and compressed. It might be one aspect of a deeper geometric structure that has no independent existence. Or it might not be fundamental at all, but something that emerges from the collective behavior of more basic elements of reality. Each of these possibilities is consistent with everything we have observed, which means that the question remains open not because we lack data, but because the data allows multiple, equally valid ways of understanding it. And that is the extraordinary situation we find ourselves in. We know that time bends. We know how it bends. We know how to measure it, predict it, and use it. But we do not yet know what it is that is being bent. And until we do, the simple act of standing in a room, feet on the floor, head on a pillow, remains one of the deepest experiments in physics, quietly unfolding at a rate set by the gravity beneath you. Part 11. The Quantum Edge of Time. There is a point, if you follow this story far enough, where the questions stop feeling like questions and start feeling like pressure, not confusion pressure, the kind that builds when every piece of evidence lines up cleanly, when every experiment agrees, when the equations work with almost unsettling precision, and yet the meaning underneath all of it refuses to settle into a single, stable picture. That is exactly where modern physics finds itself. On one side, you have general relativity, a theory so successful that it can predict how much slower time runs at your feet than at your head and be confirmed down to differences measured across a single millimeter. It treats gravity not as a force, but as geometry, the curvature of space-time itself. Massive objects don't pull things toward them. They reshape the structure of reality so that all paths lead inward. On the other side, you have quantum mechanics, a theory equally successful, equally precise, but built on a completely different set of assumptions. Instead of smooth geometry, it gives you uncertainty. Instead of definite trajectories, it gives you probabilities. Instead of a continuous space-time, it suggests a world where the smallest scales are governed by fluctuations, superpositions, and discrete interactions. Individually, both theories are astonishingly accurate. Together, they don't fit. And nowhere is that mismatch more revealing than in the question of time. General relativity assumes that space-time is a continuous fabric, a smooth, differentiable structure that can be bent and curved. Time is built directly into that fabric as one of its dimensions. It flows, it stretches, it slows down in gravitational fields, but it is always there, part of the underlying stage on which everything else unfolds. Quantum mechanics, however, doesn't treat time the same way. In its standard formulation, time is not an operator like position or momentum. It's an external parameter, a kind of background clock that ticks independently of the system being described. The equations evolve in time, but they don't explain what time is. It's assumed, not derived. This difference might seem subtle at first, but it becomes a serious problem the moment you try to combine the two frameworks into a single theory of quantum gravity. Because you can't have one theory where time is part of the system and another where time is outside the system and expect them to merge cleanly. And when physicists tried to force that merger, when they took the mathematical machinery of quantum mechanics and applied it to the gravitational field itself, they got something deeply strange. They got an equation where time disappears. This is the Wheeler-DeWitt equation, one of the central results of canonical quantum gravity. It's meant to describe the quantum state of the entire universe, everything, not just particles within space-time, but space-time itself treated as a quantum object. And when you write it down, something immediately stands out. There is no time variable in it. Not hidden, not implicit, just gone. The equation has the form of a constraint rather than an evolution. Instead of telling you how a system changes over time, it tells you that the total energy of the universe, when everything is accounted for, adds up to zero. The quantum state doesn't evolve. It doesn't move from past to future. It simply exists as a static solution. At first glance, this feels like a mistake. Time is one of the most basic features of experience. Everything we know seems to unfold within it. How could a fundamental equation describing reality not include time? But the mathematics is consistent, and that forces a shift in perspective that is hard to overstate. If the most fundamental description of the universe has no time, then time is not fundamental. It has to come from somewhere else. This is what physicists call the problem of time in quantum gravity. And it's not just a technical issue, it's a conceptual rupture, because it suggests that everything we've been discussing, the slowing of time in gravity, the bending of temporal rates, the idea that falling is following time might not be describing a fundamental ingredient of reality, but a derived one, a secondary effect. something that emerges under certain conditions, rather than something that exists at the base level. So where could time come from? One of the most compelling ideas is that time emerges from correlations, specifically from quantum entanglement. In the 1980s, physicists Don Page and William Wooters proposed a way to recover the experience of time from a timeless quantum state. Their idea starts with a simple but radical shift. Instead of thinking of time as something external that systems evolve through, you treat the entire universe as a single, static quantum state. No external clock. No background timeline. Then you divide that universe into subsystems. One subsystem plays the role of a clock. Another plays the role of the system you want to study. Even though the total state is static, the correlations between these subsystems can create the appearance of evolution. When the clock subsystem is in one state, the system subsystem is in a corresponding state. When the clock changes, the system appears to change with it. From the inside, it looks exactly like time is passing. But nothing is actually evolving at the fundamental level. What you're seeing is a pattern of correlations, a structured relationship between parts of a larger, timeless whole. In this picture, clocks don't measure time. Clocks create time by establishing correlations that can be interpreted as temporal order. That alone would be a profound shift. But recent theoretical work pushes the idea even further. In 2025, researchers exploring the intersection of quantum thermodynamics and information theory arrived at a striking conclusion. Measuring time is not free. Any physical clock, no matter how advanced, must pay a minimum cost in terms of entropy production. The more precisely you want to measure time, the more disturbance you must introduce into the system. In other words, there is a fundamental limit to how cheaply time can be defined. This connects directly back to the idea of time as something emergent. If measuring time necessarily alters the physical state of a system, if it requires energy, produces entropy, and changes the information content of the environment, then time is not just sitting there waiting to be read. It is, in a very real sense, being constructed through physical processes. Every tick of a clock is not just a passive observation. It's an active interaction with the universe. And that raises a deeper question. If time emerges from correlations, and those correlations require physical processes to be established and maintained, then what we call the flow of time might not be a fundamental flow at all. It might be a reflection of how information is structured and exchanged at the quantum level. That idea gains even more weight when you look at one of the most ambitious experimental proposals in modern physics, the Bose-Marletto-Vedral (BMV) experiment. The goal of this experiment is deceptively simple. Take two small masses, place each of them in a quantum superposition of positions, and allow them to interact only through gravity. If gravity is classical, if it behaves like a smooth field with no quantum properties, then the two masses should not become entangled. They should remain independent. But if gravity is quantum, if it can carry information in the way other quantum fields do, then the gravitational interaction should entangle the two masses. That entanglement would be measurable, and if it's observed, it would be the first direct evidence that gravity itself is a quantum phenomenon. Why does that matter for time? Because if gravity is quantum, and if space-time geometry arises from quantum processes, then the curvature we interpret as gravitational time dilation might not be a fundamental bending of a pre-existing temporal dimension. It might be a large-scale manifestation of underlying quantum correlations. This connects to one of the most provocative ideas in theoretical physics, the conjecture known as ER equals EPR. It proposes that space-time connections like wormholes are equivalent to quantum entanglement between distant regions. If that's true, then the structure of space-time itself is built out of entanglement, not metaphorically, literally. In that framework, what we perceive as the smooth geometry of space-time including the gradients in time that we call gravity, emerges from the pattern of entanglement in the underlying quantum state. The bending of time is not something happening to time. It is what entanglement looks like when viewed at large scales. And suddenly, the original question shifts again. Because now you're not just asking whether gravity bends time or whether gravity is time. You're asking whether both gravity and time are secondary phenomena, different faces of a deeper, more fundamental layer of reality, where neither concept exists in the way we usually understand it. What makes this situation so remarkable is that, despite all these radically different interpretations, the experiments remain silent on the deeper issue. The Pound-Rebka experiment confirms the gravitational redshift exactly as predicted. Atomic clocks flown around the world behave precisely as general relativity says they should. GPS satellites correct for time dilation with microsecond precision. Optical lattice clocks measure differences across millimeters. Every measurement agrees. But none of them can tell you why time behaves this way. They reveal the structure of the phenomenon with incredible accuracy, but they do not distinguish between interpretations. Whether time is fundamental, geometric, or emergent, the predictions are the same at every scale we can currently probe. That's what defines a true frontier in science. Not confusion, not contradiction, but a situation where multiple, deeply different explanations all fit the data perfectly, and there is no experimental way, yet, to choose between them. So we are left in a position that is both precise and incomplete. We know, with extraordinary confidence, that time does not run at a universal rate. We know that gravity creates measurable differences in the passage of time, even across the smallest distances. We know how to calculate those differences, how to test them, how to build technology that depends on them. But when we ask the deeper question, what time actually is, at the most fundamental level we reach the edge of what current physics can answer. And beyond that edge, there is no settled picture, only competing frameworks, each internally consistent, each supported by the same body of evidence, each offering a different vision of what reality might ultimately be made of. That is not a failure of science. It is what progress looks like when you get close to the foundations. Because sometimes, the most important discovery is not a new answer, but the realization that the question itself goes deeper than you thought. Part 12. The rate set by the world. Let us come back to the room. You have been sitting in it, or standing in it, or lying in it this entire time, and somewhere along the way something subtle happened to your perception of it. Not because the room changed in any physical sense. The walls are still where they were. The ceiling has not shifted. The floor has not moved. And yet, once you accept what the experiments of the last century have quietly forced us to accept, the room stops being a simple piece of architecture. It becomes something stranger. It becomes a slice of space-time that is not uniform, not neutral, not evenly shared by everything inside it. Because now the room is no longer just space, it is time with a shape. The floor is not merely below you in a geometric sense. It is deeper in the gravitational field of the Earth than the ceiling above you. That difference, though almost unimaginably small, is real. And because of it, time does not pass identically everywhere in this room. The atoms in the floor are ticking ever so slightly slower than the atoms in the ceiling. The atoms in your feet are ticking ever so slightly slower than the atoms in your skull. The difference is not something you can feel. It is not something your nervous system could ever evolve to detect. But it is something that has been measured repeatedly in laboratory conditions where clocks are precise enough to resolve changes that would otherwise remain invisible. The magnitude of this effect in a typical human-sized room is on the order of parts in 10 to the 14th between floor and ceiling. That number is so small that it collapses intuition. It is a difference so slight that if you lived your entire life trying to sense it directly, you would never even get close. And yet it is not hypothetical. It is not a theoretical artifact. It is the same effect that has been confirmed in experiments beginning with the pound Rebka measurement in 1959, refined through decades of atomic clock comparisons, and now embedded into the functioning of global positioning systems that would fail completely without correcting for gravitational time dilation. This is where the room stops being ordinary, because there is no longer a single time in it. There is only a field of slightly different times, layered across height, position, and gravitational depth. The universe does not assign a single universal clock to this room. It assigns every point its own proper time, and those times do not agree perfectly with one another. They are related, yes, by precise mathematical rules, but they are not identical. And that distinction changes everything about what it means for anything to happen inside this space. This is not an engineering problem. It is not a measurement error. It is not something waiting to be corrected with better technology. It is structural. It is built into the geometry of reality itself. There is no universal clock running behind the universe, no cosmic metronome against which everything is synchronized. That idea, Newton's absolute time, turns out to be an approximation, a deeply useful one at human scales, but not the underlying truth. The real structure is more fragmented, more local, more dependent on where you are and how fast you are moving relative to everything else. Every clock is local, every rate of time is specific to its position in space-time, and the relationships between those clocks are not governed by a master timekeeper, but by geometry. The geometry of space-time, shaped by mass and energy, determines how time is distributed. It determines how fast or slow it runs from point to point. And in doing so, it turns time into something that behaves less like a universal background and more like a terrain. And you are not outside that terrain. You are inside it. From the moment you were born, the earth has been shaping the rate at which your life unfolds, not in a metaphorical sense, in a literal, physical, experimentally confirmed sense. The closer you are to the earth's mass, the slower your time runs compared to someone farther away. That means every second of your existence has been measured out in a slightly curved temporal field shaped by the planet beneath you. The effect is small, but it is cumulative and real. Over the course of a human lifetime, the difference in elapsed time between your feet and your head amounts to an extraordinarily tiny fraction of a second. But that fraction is not zero. It is not symbolic. It is physical difference accumulated through every heartbeat, every breath, every neural impulse that has occurred in your body since you came into existence. Even within your own body, time is not uniform. Your feet age at a marginally different rate than your brain. Your organs are not synchronized in a perfectly rigid temporal unity. They exist within a gradient of time, stretched across your height, continuously shaped by the Earth's gravitational field. The chemistry in your cells, the firing of neurons, the slow processes of biological decay and renewal, all of it unfolds in slightly different temporal frames, depending on position. And yet, your experience of yourself is seamless, continuous, unified. That, in itself, is part of the mystery. Because physics is telling you that you are not a single point in time. You are a distributed object across a field where time varies. And yet, consciousness presents you with the illusion of a single flowing present moment. That mismatch between physical structure and lived experience is one of the most profound gaps in our understanding of reality. So what exactly is being bent? This is where the clean, empirical clarity of physics meets the unsettled ambiguity of interpretation. Because the experiments are not in question. The pound Rebka experiment measured gravitational redshift exactly as predicted. Atomic clocks flown around the world confirmed time dilation with extreme precision. GPS satellites correct for relativistic effects every second of their operation. Optical lattice clocks can now detect gravitational differences across millimeter-scale height changes. The data is consistent. The equations work. But the meaning behind those equations is not uniquely determined by the data. One interpretation is that time is a kind of real, physical entity, something like a river that flows differently depending on gravitational conditions. In this view, gravity is literally a slope in the flow of time. Mass creates curvature in this temporal river, and objects move through it according to that curvature. The sensation of weight, then, is not a force in the traditional sense, but the experience of being constrained from following the natural flow of that curved temporal structure. But this raises an immediate question. What is this river made of? What is its substance? What carries it? And what does it mean for something so fundamental to vary in rate across space without any underlying medium we can identify? A second interpretation avoids that problem by denying that time is a substance at all. Instead, time is treated as part of geometry itself. Space-time is a four-dimensional structure, and time is simply one of its dimensions. In this view, gravity is not bending an independent thing called time. It is shaping the geometry of space-time as a whole. Time does not exist separately from that structure. It is a coordinate, like a direction in space, defined by relationships within the geometry rather than by any underlying physical substance. But even this interpretation leaves something unresolved, because geometry itself becomes the fundamental entity, and we are still left asking what that geometry represents physically. Which leads to a third possibility, one that sits at the frontier of modern theoretical physics. In this view, time is not fundamental at all. It does not exist at the deepest level of reality. Instead, it emerges from more basic processes, likely quantum in nature, possibly involving entanglement, correlations, and information flow. In this picture, space-time itself is not primary, it is emergent, and time is a large-scale approximation of underlying quantum relationships. What we perceive as the flow of time is a macroscopic pattern arising from the structure of entanglement between quantum states. There are hints of this idea in approaches like the Wheeler-DeWitt equation, which describes the quantum state of the universe without any time parameter at all. There are further hints in modern research connecting space-time geometry to quantum entanglement, where connections between distant regions of space may be equivalent to patterns of quantum correlation. If this is correct, then gravity is not bending time in any fundamental sense. It is shaping the structure of quantum information, and time is the emergent description of that structure when viewed at large scales. The striking thing is that all three interpretations agree on every measurable outcome we currently have access to. Whether time is a river, a coordinate, or an emergent pattern, the predictions for experiments like Pound, Rebka, GPS corrections, or atomic clock comparisons are identical. This is why the question remains open, not because the physics is uncertain, but because the physics is underdetermined at the level of interpretation. The data tells us how time behaves. It does not tell us what time is. And so we return again to the room, because this is where the abstraction becomes immediate. You do not live in a uniform flow of time. You live in a structured gradient of it. The floor beneath you, the ceiling above you, your feet, your head, all of them are embedded in slightly different temporal rates shaped by the Earth's mass. The sensation of standing, of weight, of stability is intimately tied to this structure. Gravity is not just something pulling you downward. It is the manifestation of the geometry that determines how time is distributed in your immediate environment. When you drop an object, it does not fall because it is being pulled in the everyday intuitive sense. It falls because it is following the structure of space-time, which is itself shaped by the distribution of mass. Its path is a trajectory through curved time as much as curved space. The same is true for satellites orbiting Earth. The same is true for planets orbiting the Sun. The same is true for light bending around massive objects. All of it is geometry expressed dynamically. And in that sense, gravity is not an external force acting on the universe. It is the structure of the universe itself. We know how this structure behaves. We know how time bends, how it dilates, how it shifts across height and velocity. We have measured it with extraordinary precision, and we have built technologies that depend on those measurements being correct. Civilization itself now quietly runs on relativistic corrections. But we still do not know what time is, such that it can do any of this. And that is where the room becomes something more than a room again. Because standing in it, or sitting in it, or lying in it, you are not simply occupying space. You are occupying a region of curved time. Every moment you experience is being shaped by the mass of the planet beneath you, by the geometry of space-time, by whatever underlying structure ultimately gives rise to the phenomenon we call duration. The Earth has been doing this for billions of years. Long before clocks, before language, before life itself, it was already shaping the rate at which time passed near its surface. And it will continue doing so long after every human artifact has disappeared. The bending does not require us. It does not depend on observation. It does not wait for interpretation. It simply is. And you in this room are inside it right now.